So, did you ever want to implement a fog of war feature for one of your strategy games in Godot? Like the typical RTS system that hides parts of the map until your units have explored them and gradually reveals the other buildings and relevant objects? You know, something like you'd get in Warcraft, for example. Okay, so in this tutorial, we'll be working in a 3D scene like this one. Overall, it's pretty similar to the ones I've used in my recent other episodes on RTS features, and by the way, feel free to have a look after you've watched this one if you want to learn more about how to select or move units and how to place buildings. But so, anyway, in this scene, I've got some 3D objects that make up my environment, so the ground patches, the trees and rocks, and the water plane. And then I've got this other hierarchy specifically for this demo. That's because in this video we'll focus on the fog of war, but as you probably know, this means that we still need some units to move around the map to actually explore the world and impact this fog of war. So to keep it simple, I've prepared two 3D paths that two units will move along thanks to this animation player node, and so basically with this animation that autoplays as soon as the scene starts and loops, our two ships will travel across the water in the middle of the map. Oh, and also I put those two tower buildings over here and over here, so that we can add and test the extra reveal buildings during exploration mechanic of our fog of war system. The final important part of this scene is the bunch of nodes that will actually handle the fog of war. Those are in fact user interface nodes that are in this HUD sub-hierarchy, and more specifically, as you can see, we've got a global UI node that adds a bit of spacing to our interface, a control that is just here to allow us to easily resize the stuff inside, and finally, the real thing we're interested in, this panel container, along with its two child nodes. So the idea is that these three nodes will allow us to compute and visualize our fog of war in real time, in the top left corner of the screen. Our fog of war will be stored and updated as an image. It will be a grayscale mask that determines which areas are currently in view for units, which ones have been explored, and which ones are still unknown. Each unit will have a sort of fog of war mask stamp that moves along with it, and little by little adds white to the original black image to keep track of the previous movements and reveal new zones. Okay, but so first of all, let's take care of creating and updating this fog of war image. The size of this 2D image will be given by the size of the panel container node, which here is 512 by 512 pixels, and then we've got our update timer node that will send its timeout every 0.1 second. Of course, you can totally make it faster, but remember that the more fog of war updates you ask Godot to do, the more taxing it will be on your computer. And typically, the fog of war is usually something that can be a bit chunky in its update, without players noticing or caring too much, so keeping the timer to this kind of update rate isn't too crazy. The last node is the base texture rect. This is the node that will show our computed fog of war image in-game, to allow us to check what it looks like and track its evolution as our units move around the map. And in fact, with this pretty basic setup, we've already got everything we need to create a basic first version of our fog of war system, which is done by the script on our FOW node called FOW, and that looks like this. At the very top of the script, we have two variables. The map size, which is exported and thus editable in the node's inspector, is a level-specific metadata that we'll need to set up manually to tell the script what the horizontal dimensions of our scene are. This will be key in letting us go from 3D world positions in our scene to matching 2D coordinates on our fog of war image, when we want to actually compute and then reapply our fog of war. Typically in my scene, all my environment asset is encompassed in a 50 by 50 unit square. So this is what I'm gonna put for my map size property in the FOW node inspector. Then in the ready function, our script sets up the fog of war image, debugs it into our texture rect node, and links our update timer to the update function before starting it. To set up the image, we've got this simple makeImage function that creates a new image resource based on the size of the FOW node, as we said before, and fills it with black pixels. We can use the alpha parameters to choose if we want these initial pixels to be black or transparent. And that's why, to be sure our image handles transparency, I've used the RGB-A format that has an alpha channel. The update function, that will be called regularly by our update timer, is where we actually use our current unit positions to update our fog of war image. Basically, the idea is that, in my unit scene, I've added this F4W texture rec node that uses a simple blurred white circle sprite. This is the fog of war mask stamp that I talked about before. Also, as you can see in its inspector, this node has a size of 128 by 128 pixels. This may or may not be the exact size of the texture inside. Here, typically, my image is actually 64 by 64, but Godot can have this node stretch despite the sprite's original size, and again, in our case, it's not really a big deal if the stamp is a bit blurry. The other important thing is that our F4W node is added to a special nodes group in the project, for example, here one called Unit F4W. This will allow us to quickly iterate through all the Unit F4W mask stamps in the scene when we update our fog of war image, to know where they are and how they should carve out our mask. And of course, since we'll be reading this texture rect data from our script, we can, and we actually should, hide it so that it doesn't directly show in the scene. As a final note, when creating and importing your fog of war mask stamp sprite, you should make sure of 3 things. First, it should be a transparent image, where the white represents the shape to carve out of the fog of war image as the unit explores the world. Then you should make sure that the sprite is not compressed, which you can do by double-clicking the resource and then going to the import settings panel, selecting the VRAM uncompressed import mode, and clicking the re-import button. Finally, you'll see that in the sprite inspector, Godot tells you its format. This is the format you need to be using for your fog of war image, so in the make image function, because as we'll see soon, we'll be blending those 2 images together, and so they need to have the exact same format. Alright, and now with all this in mind, let's go back to our F4W script and study our update function a bit. Now you know that this for loop iterates through all the F4W mask stamp texture recs throughout the scene, hooked to every unit. These 3 steps convert the global 3D position of the unit to the equivalent 2D position in our fog of war image. Basically, what we want to do is isolate the X and Z components of the 3D position to get the horizontal data, then offset it by half the map size to have the coordinates go from 0, 0 to the map size, instead of having the origin in the center. And finally, this line gets the normalized horizontal position of the 3D unit, multiplies it by the fog of war image size to put it back in this coordinate system, and finally offsets it a little bit to recenter the mask stamp position properly. Then all that's left to do is to access the sprite on a unit's F4W texture rect node, get the corresponding image resource, optionally resize it if our texture rect isn't the same size as its sprite texture, and use the built-in method blendRect to mix it with our previous fog of war image. So what this line does is it takes the current fog of war mask and at the 2D position matching the 3D world's position of the unit, we're applying fog of war 4, it passes the stamp mask onto the existing pixels. And this part tells Godot to take the entire stamp mask texture area. Okay, so after this loop, we've basically updated our grayscale fog of war mask so that every unit in the scene has carved out a bit of fog around itself. Finally, we just use our updateTextUtil method to reconvert the updated image resource to a texture and show it in our texture rect node in the top left corner of the screen. And there we go! If we run the game, you see that thanks to our animation, the units indeed move in the scene on their own, and as they glide on the water, our fog of war 2D image updates accordingly by tracking their movements gradually over time as a white mask. Alright, so this is cool, but now the question is, how can we actually use this 2D image and apply it onto our 3D scene to really show the fog of war to the players? Well, here we're actually going to rely on a pretty nice technique that uses a post-processing shader. In a nutshell, the idea is that rather than giving each and every node in our 3D scene a shader that reacts to the fog of war mask, we'll rather let our game compute it as a post-processing effect on top of the render. This way, we'll be able to handle even pretty complex scenes with lots of stuff in it really easily. Though in our case, because this water plane uses a really cool shader by Royston that is a bit more advanced than the rest of the objects, we'll need to do just one exception and take care of the fog manually for this shader. So first of all, let's make sure that both our post-processing shader and our water shader can access our fog of war texture and the map size quickly. And for that, we're going to take advantage of a neat feature of Godot 4, the shader global variables. Basically, if you open up your project settings panel and you go to the Globals tab, then the Shader Globals subtab, you'll be able to pick a type for a global uniform variable and then give it a name over here and add it to the list. In our case, we'll have a sampler to the uniform called FOW texture and a vector2 called map size. We could set the values over here, but we can also set them dynamically at runtime super easily in our FOW script by using the rendering server API, and in our case the map is always the same, so we can set it just once in the ready function, but of course the fog of war texture evolves over time, so we'll update it when we update our debug texture as well. So at that point, any shader in the project can access those two global uniforms. So time to work on our post-processing fog of war effect. Now, to give you the gist, what we're going to do is use the depth texture that Godot computes whenever we render a 3D scene to convert all the pixel positions on screen into their equivalent 3D world positions. And then we'll sample our global fog of war texture to know if, at this position, our mask is black or white. If it's white, then it's carved out, and so we'll just keep the rendered image as is, effectively ignoring the fog of war. But if it's black, meaning we haven't explored that point yet, we'll overlay our render with some black to hide everything for the players. Okay, so first of all, to make sure our shader can use the depth texture, we need it to be a spatial shader. And to still have it work as a post-processing effect, we can follow the little full-screen quad trick shown in Godot's documentation. In short, we're going to create a mesh instance 3D node inside a scene that has a quad mesh. We'll give this quad a size of 2x2, and we'll enable its flip faces option. And then on this new mesh instance 3D node, we'll create a new material that uses our custom fog of war post-processing shader. Now, as we said, this shader is spatial, it works on 3D nodes. We'll also make it unshaded because we don't want our post-processing quad to use any lighting. And at the top, we get back our two global uniforms, so the fog of war texture and the map size. Then we also get two textures that Godot autocomputes for us, the screen texture, which is the current rendered frame, and the depth texture that contains depth info, or in other words, the distance to the camera for every object in the scene. Then we've got the vertex function, which is the final thing that ensures our quad actually is full screen and creates a post-processing effect. And finally, the real magic comes from the fragment function. These few lines allow us to transform our 2D screen point into its equivalent into the 3D world, basically by projecting it from the camera, using our depth texture to know how far the ground is. And the last three lines use this world position to get the proper value for the fog of war. Just like before in our script, we'll use the X and Z components of the point to get the horizontal position, and remap it so it's not centered on the 2D scene origin anymore. Then we divide it by the map size to renormalize our point and get 0 to 1 values for 2D vector. Those simply give us the UV coordinate that we need to sample our fog of war texture at, just as if we were projecting this texture onto our scene from straight above. And so last but not least, we just multiply our initial rendered frame by the fog mask to make the unexplored areas pitch black. Something important to remember, however, is that the depth texture is only accessible if your camera uses perspective and not orthographic projection. So if you want to mimic the typical RTS orthographic view while using the perspective projection pipeline, you can just decrease the FOV angle to something very low, like 10 degrees or less, and move back your camera far away from your scene. For the water shader, as I said before, it originally comes from Royston, but this is a Godot adapted version from this really cool GitHub. And so to add the fog of war to it, I just used the same commands to re-import my global uniforms, And then at the very bottom, at the end of the fragment function, I sampled my fog of war texture and multiplied my color by this value and forced the alpha to 1 if the zone is unexplored. The reason I can use the UVs directly over here to sample the texture is because my water plane is a horizontal plane that covers the exact size of my map, so basically all of the computations we did before give us the exact same UV as the default UV coordinates of the plane mesh itself. But in any case, that's it. If we rerun the game now, you'll see that at first everything is black, cause our fog of war image starts off completely black, but then, as soon as our units move around and update this mask, the new image is used as the new global texture in our shaders, and our terrain is gradually revealed. And of course, if our units go through the same path, the mask has already been carved out, and so our fog of war doesn't really change anymore. Okay, so this is starting to look very nice, but there is a cool improvement we should do on that system. Cause right now, once a unit has left an area, the area remains fully lit, contrary to a lot of RTS games where, as we discussed before, we've got an in-between state of explored, but not currently watched, areas. To do this, the trick will be to change our mechanic a little bit, so that instead of having just black and white in our mask, we also have grey pixels, like this. And since in our shaders we sample the FOW texture and multiply our colors by it, this will work automatically and turn this intermediary color into dimly lit parts in the 3D scene. Now, to differentiate between currently visible and already explored areas, what we're going to do is modify our FOW node hierarchy a little. Indeed, by using those extra nodes, we'll be able to support our 3 fog of war states. The subviewport node will allow us to dynamically get a texture that isn't just the current content of a single texture vector, but instead of all its child nodes at the same time. So here, this will allow us to get, as an image, the overlapped visuals of our base and our current texture vector nodes. The base node will contain the info about the already explored areas, meaning it will have a mask that keeps track of everything that has happened and gradually carves out the mask. We'll use its self-modulate property to make it a dark grey so that it creates those intermediary values in our final fog of war image. The current node, on the other hand, will contain the info about the currently visible areas, meaning that it will be a very dynamic image that doesn't stack the stamp movement over time, but just displays the little white areas matching the fog of war stamp of the unit at this specific time. The subviewport container node, above the subviewport, is just a way to display this subviewport in our UI, so that we can keep debugging our result. And also, note that I've moved our FOW script from the panel container to this subviewport node, so that the texture nodes inside remain easily accessible. Okay, so let's see how to update our FOW script to handle all of this. First of all, because we've moved our script over to our subviewport node, we should make sure to update the first line of our script to say that it now extends the subviewport class. And now to create our new image, by updating and overlaying the 2 texture vector nodes, we just need to do 2 things. One, in the update function, we'll create our dynamic image for the current texture. We'll again use our makeImage function, except this time we want it to start off as transparent with an alpha of 0 so that it will show above the base texture and doesn't just cover it. Then, whenever we add a unit FOW mask stamp on our long-term image, the one for the base texture vector, so the globally explored areas, we'll also add it to our temporary image for the currently visible areas. And finally, we'll use this dynamic image to create the proper texture for our current texture vector node. 2. In the update text function, we'll still update our base texture vector as before, but for the final fog of war image, instead of using just this texture, we'll call the getTextureBuiltIn method on our scripts node. Remember that this script is now on our subviewport node, and so this getTexture function is a quick way to get an instant render, or snapshot, of whatever this subviewport contains, in our case, our 2 texture vectors overlaid. And here we go! If we run the demo, you'll see that our system now properly differentiates between currently visible zones that are fully lit, already explored zones that are more dim, and of course, unknown zones that are still pitch black. And to wrap up this tutorial, let's quickly see how to add one last mechanic, the building or object reveal, as soon as they enter a unit's field of vision. Now, if you want to make this feature, a basic approach you might try is to give your units and the objects to reveal some 3D trigger areas so that you can check if an object suddenly is close enough and should become visible. But as we said in some of the previous videos, RTS are often supposed to handle a pretty big amount of units on screen, and everything that is related to physics can quickly break your game's performance. So here, how can we avoid this problem? Well, if we take a look at the fog of war image we're gradually computing at this point, you'll notice that there are basically three types of pixels: the black pixels, the grey pixels, and the white pixels. We know that everything that hasn't been explored yet is for black. And since we want our objects to appear as soon as we've explored the map around them once, this corresponds exactly to the following idea. If the object 3D world position, once converted to a 2D position on our fog of war image, falls on a pixel that isn't completely black, then it should be visible. In other words, to implement this last feature, we just need to do a couple of things. First, we need our buildings and objects to be able to access our fog of war image and the map size. And although we could technically use the rendering server API for that, this can be quite costly if done often. So instead, let's create a new super basic script like this, for example called globals, with all two variables, and we'll register it as an autoload in our project. This way, we'll be able to set it from our FOW script like this, and then reaccess it afterwards. Then we also need to know when the fog of war image has been updated, so that our buildings only recheck for visibility when need be. For that, a nice solution is to use a global event. Let's again make a basic script like this one with our signal inside, and the script will be called, for example, events. We'll register it as an autoload as well, and back in our FOW script, in our update function, at the end, we'll emit this global signal like this. And now, all that's left to do is to give our buildings a script that uses all this data to toggle the visuals on when it's first discovered. So, suppose that I've got a very basic scene for my tower building, like that one. It only contains visuals and the root node has this script on it. In here, you see that we first connect a callback to our global event, stored in the events autoload, and we hide our object by default. Then, whenever we get an update on our fog of war, and the signal is therefore emitted, our callback function will use the global's autoload to fetch the current fog of war image and map size, and do something almost identical to our computations from the FOW script. So with these lines, we get our object's position converted to matching to the point on our fog of war image. Finally, we sample the image at this position to get the pixel color, and if any of the components of this color is above 0, it means that the pixel is not black, and thus this area of the map has been explored and our building should be visible. Of course, because we want it to remain visible forever from that point on in the scene, we can then just unhook our callback function from the global signal to avoid triggering useless logic. And well, that's it. With this new mechanic in place, we've now got a full RTS fog of war system that properly uses unit positions to evolve over time, handles 3 different states, shows relevant objects once they've been discovered, and because it's based on shaders, can handle pretty complex scenes in an efficient way. But of course, there are still a lot more nice features that make up an RTS game. So if you've got some ideas of mechanics you'd like me to talk about, go ahead and leave a comment down below. And if you want to make sure that you don't miss any upcoming videos, subscribe to the channel. In the meantime, there are already a bunch of tutorials that you can discover. Of course, a huge thanks to my Patreon members for the support, and to you for watching. And as always, take care.